So suppose we start out with a simple example where we have x of t that is equal to 1 over square root a from 0 up to a. So suppose we look at this signal x of t that takes on this square shape between 0 and a. So suppose we are asked to compute the energy, okay? So the energy is the integral from minus infinity to infinity x of t squared dt. So the energy is the integral of the absolute square of x of t over the entire time horizon. But you can see that x of t is non-zero only between 0 to a, okay? So then you can limit the integral from 0 to a, and within this time duration, the signal is 1 over square root a, so the square of that is 1 over a. And if you work out this integral, this is just equal to 1. So the total energy of this signal is 1. Now, if you compute the average power, right, so this is the limit as t goes to infinity, 1 over 2t minus t to t x of t squared dt. Now, intuitively, right, you can sort of see that the average power, if you're looking over infinite time, should be 0, right? Because if you have only finite total energy and you have to average over infinite time, then the power is spread out and eventually becomes 0, okay? So to show that, so what you can do is that you can first upper bound this integral. You can first upper bound this integral by e infinity, okay? So e infinity is this integral with t extending to infinity, okay? So when you integrate a positive number over a larger range, you must get a value that is larger than this, okay? Now, e infinity is just 1. If you're dividing by something that goes to infinity, then it must be 0. So this shows that, for a finite energy signal, you must have 0 average power. Now let's look another example, right? Let's extend this example a little bit by repeating this square wave at integer multiples of a, right? And switching between positive and minus values. So here I have x of t that goes from, okay, that is 1 over square root a from 0 to a, but then has value minus 1 over square root a from a to 2a, and then positive again from 2a to 3a, and so on and so forth. So we're taking this square wave and we're repeating it every integer multiple of a, but alternating between the plus and minus signs. Okay. Now we can compute the energy of this. So the energy is the integral of the square of x of t. Okay. Now if you look at this signal here, you can see that no matter if this signal is positive or negative, the square is always 1 over a, okay? So you're integrating 1 over a over an infinite time, and therefore this integral is infinite, okay? So this signal here has infinite energy, right? But if you compute the power, the power is the average over 2t of the energy from minus t to t. Okay? And the square here is 1 over a again, regardless of what time you're looking at. Okay? So So you're averaging a constant over infinite time, and therefore the average is just the constant itself. Okay? So you can see here that this signal has finite power. This is a finite power signal, but it has infinite energy. Okay? So this is an example of a signal with finite power but infinite energy. Okay. Now let's look at one more example. We look at the case where x of t is just equal to t. Okay? So the function looks something like this. Okay? So again, we can try to compute, let's say we try to start by computing the average power. Okay? So by definition, this is just the limit of t going to infinity, 1 over 2t, integral minus t to t squared dt. Now, this t squared is symmetric about the origin, right? So we can, compute this integral from minus t to t as 2 times the integral from 0 to capital T, right? Because it's symmetric, okay? So we can write this as the limit of 1 over t, 0 to capital T, t squared dt. Okay. So if you work out this integral, you will get limit of 1 over t, 1 over 3 capital T cubed. Okay? So you can cancel out one of the t's from up here, right? And you will still have capital T squared. So then as capital T goes to infinity, this essentially goes to infinity. Okay? So this is infinite. So this signal here is infinite power, is an infinite power signal. And if a signal has infinite power, then it must most definitely has infinite energy as well. So these are just some examples of different types of signals categorized by whether or not they have finite energy or finite power. Okay? So you can sort of see from these examples that if you have a signal that is confined to a finite time period, then usually it's finite energy. Okay? If you have a periodic signal, right, a signal that repeats itself over time, then usually it's infinite energy, right, because it extends to infinite time, but it can have finite power. Okay? Now, if you have a signal that grows without bound, then usually, it will have infinite power. Okay, so this is just to sort of give you some insight on what types of signal you would see in each category. So for the Fourier analysis that we're going to learn in the next few chapters, we're mostly only able to handle either periodic signals or signals of finite energy, okay? Signals mostly confined to a certain time interval, okay? So the Fourier analysis usually does not apply to signals of infinite energy. Now, when we say that we want to examine signals right? When we want to examine something, we usually take the signal, we try to, squeeze it, stretch it, turn it around, move it sideways, so on and so forth, to look at it from different angles, okay? So this, this squeezing, stretching, right, flipping around corresponds to a so-called transformation of the independent variable when we're looking at signals, okay? And these transformations may actually occur in actual systems, and we'll see in a little while, okay? So here we're going to introduce some basic types of transformations of the independent variable, starting with time shift, which is probably the most, intuitive to understand, okay? So what is the time shift, okay? The time shift transformation, it basically corresponds to shifting the original signal, okay, either to the right or to the left in time, okay? So suppose that you have this discrete time signal x of n here, okay? So suppose you have this original signal x of n here. Now, performing a time shift, right, moving this signal to the right by a certain amount, let's say n naught, corresponds to a transformation of the time of the independent variable equal to n minus n naught, okay? So this is saying that if your original signal x of n looks like this, then the signal x of n minus n naught, right, this signal with a time shift transformation, will correspond to the signal shifted to the right by n naught, assuming n naught is positive, okay? Now, how do you verify this? All right, so this is assuming that, n naught is positive. Now, how do you see that? All right. So this is because suppose you look at the value of xn at time 0, okay? So in the original function, when you observe the value at time 0, the value you see is x of 0, right? So the value you see here is x of 0, okay? Now, where do you observe the value x of 0 in this time-shifted version, okay? So the function now is x of n minus n0. So you observe the value x0 when n is equal to n naught, okay? So when n is equal to n naught, plugging this inside gives you the value x0, okay? So this point here is x of n naught minus n naught, which is x0, okay? So you can also make the same observation for other points as well, okay? So you can see that, making a transformation from x of n to x of n minus n naught, right, you're shifting the signal to the right by n naught, assuming n naught is positive, okay? Now, if n naught is negative, right, if this n naught is negative, then this would be shifting to the left instead, okay? So here we have one of those examples in continuous time, right? So suppose your original signal is x of t that looks like this. Then if you make the transformation to x of t minus t naught, where t naught is negative, then you will be shifting this to the left by this negative value t naught, okay? Okay? So you can observe this by, again, looking at, for example, the value of x0, okay? So in this continuous time signal, you observe the value x of 0 at time t equal to 0. Now, if you look at this transformed signal, when do you observe the value x of 0? Right. You observe the value x of 0 when t is equal to t naught. Okay? So when t is equal to t naught minus t naught is 0, so this value here is x of 0. Now, this time shift transformation you can observe in many practical systems, many of which are related to radar type applications. Okay, so in radar you may have this you may have this radar system that emits a signal to the air and tries to observe the reflection of the signal if there is a certain aircraft in the air, right? So, for example, you may have this radar system and the aircraft here. Okay, so you may emit a signal x of t over the air. Okay, and you will observe a reflection of the signal back to the system, if there is an aircraft existing. Okay, so what you observe here is x of t minus t naught, where t naught is the propagation delay. Right? T naught is the time that it takes for the signal to travel to the airplane and then back. Okay. So what you observe here is a time-shifted version of what you transmit. Now, another basic transformation is time reversal. Okay? So time reversal is just taking the original signal and looking at its mirror image, right, or its reflection about the origin. Okay? So mathematically, the time reversal of a signal x of n is just x of minus n, right? It's just x of minus n, okay? And this is because if you are looking at a signal, if you're looking at a signal value at a particular time n, right? At a particular time n, then when you take, after the time reversal, this value will be observed at the index minus n instead of the original index n. Okay? So if you're looking at this value at time index, let's say n naught, okay, then after time reversal, this same value will be observed instead at time instant minus n naught. So this is an example in continuous time. So similarly, if you are observing a value at some time t0, right, t naught, so this is x of t naught, okay? Then after time reversal, this same value, x of t naught, is observed at the time minus t naught. Okay? Right, so this is very simple, right? Time reversal is just flipping the signal about its origin, okay? And mathematically, it's expressed with an additional negative sign in front of the independent variable, okay? So an example that's given in the textbook is, a tape recording played backwards, okay? So I don't know if you know what is a tape these days, but basically, if you just play something backwards, then you're essentially looking at a time reversal of the original signal. Now, the third kind of basic transformation is time scaling. Okay, so time scaling corresponds to the compressing or the stretching of your original signal. Okay. So suppose that x of t is your original signal, right? Then if you multiply the independent variable by 2, right? Let's say you instead look at x of 2t, then what you're looking at is actually a compressed version of your original signal. Okay? Now, why is that the case? All right. So suppose that you're looking at the value, okay, at the point A. Okay? So suppose you're looking at the value at the point A, which is x of A. Okay. Now, in this time-scaled signal x of 2t, when do you observe this x of A? Right. You observe x of A when t is equal to a over 2, right? So when you plug in t equal to a over 2, you get x of A. Okay? So for this transformed signal here, you observe x of A at time a over 2. Okay? So by multiplying the independent variable by 2, you're sort of squeezing or compressing the signal by 2 times. Okay? So it's like everything is occurring faster than its original signal. Okay? Now, if you instead, multiply your independent variable by 1 over 2, by a value less than 1, right? Let's say 1 over 2, then when do you observe this value x of A? Right? You observe the value x of A when t is equal to 2a, right, instead of a. Right? If you plug in t equal to 2a, what you get here is x of A. So the value x of A here is instead observed at time 2a instead of the original time a. Okay? So effectively, what you're doing is stretching the signal by 2 times. Okay? So by dividing the time index by 2, what you're doing is stretching the signal. Okay? So this may be a little bit counterintuitive, right? Because multiplying compresses it, but dividing stretches it. Okay? But to me, an easy way to understand this is that when you multiply the time index by a value greater than 1, right? Let's say you multiply t by 2. This is like fast-forwarding your signal, right? So if you think of x of t as some music signal that you're listening to, then multiplying the time index by 2 is like fast-forwarding the music that you're listening to, okay? So now instead, if you divide the time by 2, then the time is progressing slower, right? So this is like playing a video in slow motion, okay? So it stretches the signal out, okay? All right, now combining all of the 3 different basic transformations, you can generally, perform a transformation that can be written like this, right? Be written as x of alpha t plus beta, okay? Now the beta here corresponds to a time shift, whereas the alpha here, depending on whether you choose alpha to be greater than 1 or less than 1, corresponds to the compression or stretching of the signal. And depending on whether alpha is positive or negative, right, you may have original signal or its time reversed version. Okay? So this is actually summarized here. So if you have alpha less than 1, then you're stretching the signal. If you have alpha greater than 1, then you're compressing the signal. If alpha is less than 0, then, aside from the stretching and compressing, you have a time reversal. And with a non-zero beta, you have a time shift. Okay, you have a time shift. So we have 5 minutes. So let's look at an example here. So suppose that our original signal x of t looks something like this, right? So this is 0 and raises up to 1 at the origin, then gradually decays to 2 after 1. Okay? All right, now we want to look at what it looks like to make these different transformations of this original signal. Okay? Now let's start out with the simplest kind, which is, a time shift, okay, to get x of t plus 1. Okay? Now here we learned that, okay, if you're looking at a signal of x of t minus t naught, then the signal will be shifted to the right if t naught is positive and to the left if t naught is negative. Okay? So we want to write that signal in this form here in order to identify how to shift the signal. Okay? But here, instead of t minus t naught, we have a plus sign here. So let me rewrite this as x of t minus 1. Okay? And in this case, minus 1 would be t naught. So with a negative 1 t naught, we're basically moving the signal to the left by 1. Okay? So this signal looks like this. So this x of t plus 1 here is equal to this x of t shifted to the left by 1. And you can check if this is correct, right? So originally, the value x0 occurs at time 0, okay? Now, if you look at this function, when would the value x of 0 occur? Okay? The value x of 0 will occur when t is equal to minus 1, right? So this value that you see in the original signal should now occur at the point minus 1. Okay? So just by a simple double checking, we can see that this figure should be correct. Now, the second case is x of minus t plus 1. So x of minus t plus 1, okay? So there's a minus sign here, so this implies that we may have some sort of time reversal, right? And there's a non-negative beta, so there should be some time shift, okay? Now, if you observe the similarity between these two functions, you will see that if you view the above function as some function y of t, right? If you view this x of t plus 1 as some function y of t, then this function on the bottom is just actually y of minus t, right? So this is actually just y of minus t. So what does this mean, right? This means that this function here is just a time reversal of this function here. So we can see by comparing these two, we can see that this should be just a time reversal of this. Now, this sort of implies that when you're directly asked to find this transformation, x of minus t plus 1, it's easier to first perform the time shift and then perform the time reversal, okay, or the time scaling, okay? So this is a rule of thumb here, right? From this example, you can sort of see that to find this transformation, an easier way is to first find the time shift and then perform the time reversal. You can certainly do it the other way around, but the other way around gets a little bit, tricky, right? Because if you first do the time reversal and then the time shift, then the function you're looking at, what you're doing is essentially looking at this function here. So you're first performing the time reversal, and then for that reversed function, you're considering a time shift of 1, okay? And that gets a little bit tricky because when you first do the time reversal or time scaling, and then you want to do the time shift afterwards, then you have to take into consideration how this time shift varies depending on the scale in the front, okay? So this can become a little bit tricky, right? So I promised to end at 3, so maybe let's do this tomorrow, okay? So you'll see how this takes effect in these two examples as well, right? So it gets a little bit trickier if you do the time scaling first and then the time shift afterwards.